Thank you to the organizers for inviting me here today. Today I want to talk about how we can take mid-infrared radiation, so this is radiation on the micron scale, and integrate it with nanoscale materials and structures and molecules. So the title of my talk is then Making the Mid-Infrared Nano. In particular, I'm going to talk about how we can do that with new plasmonic and metamaterials. Of course, before I begin, I do want to acknowledge the people who actually do the work, which are my grad students here at UIUC, as well as a couple of students who finished up at UMass, where I moved from. My postdoc, Stephanie Law, who did a lot of the doped semiconductor work that I'm going to talk about. And we also work with a lot of undergrads, collaborators, and of course the people who actually paid for this work to be done. Okay, so when we talk about the mid-IR, before I say why we're interested in the mid-IR, it's probably worth defining what I mean by the mid-IR. And if you talk to someone in the military, they have very specific definitions of what different portions of the mid-IR mean. But today, I'm just going to basically say, in general, what I'm talking about is a wavelength range between 3 and 30 microns. And everything, it turns out, that has a finite temperature emits in this frequency range. So whether it's mechanical objects like a jet engine or the engine of a helicopter, or my lab group, they all are emitting thermal radiation in the mid-infrared region. And because everything emits in the mid-IR, everything also absorbs in the mid-IR. And some things absorb very nicely and very strongly in the mid-IR. In particular, there are a number of molecules that have very distinct and defined absorption spectra in the mid-infrared. That's why it's often referred to as the fingerprint region of the optical spectrum. And you can see here the absorption spectra for ammonia. And what you see is exactly that, a spectral fingerprint, a series of absorption peaks that is associated with ammonia molecules. And you can see that at these longer wavelengths, these absorption peaks, which correspond to fundamental vibrational modes in your molecule, are significantly stronger than as you go to shorter wavelengths. So why does that matter? Well, thermal emission is often used to target and track heat-emitting objects, whether those are the airplanes that I showed in the first slide, and God forbid whether it's my research group, but that heat signal can be used to track and target heat-emitting objects. So if we can control the thermal emission from a hot object, then we can either hide that object from one of these targeting systems, or maybe we can make an object that we don't care about as some sort of consumable structure that we can use to confuse the targeting system. Now, one can do that fairly easily with various different types of coatings, but what we're actually interested in is, are there ways that we can make selective thermal emitters where we control the thermal emission spectrally, but also we can control the intensity dynamically. Namely, can we dynamically control the thermal emission of a hot object, and ideally, therefore, blend it into the thermal background and thermally cloak a hot object? So that's sort of on the thermal emission side of things. In terms of the sensing side of things, what we're interested in is detecting the presence of these molecules using mid-infrared light, using this absorption signature. And to do that, you need sources, you need detectors, but you also need a way to interact your light with these molecules. These molecules are on the nanoscale, and your light is on the micron scale. So you have to figure out a way to be able to confine your optical mode in such a way that you can get strong interaction between that light and the molecule of interest. And in both cases, what we're essentially talking about is figuring out a way to get our microscale light down to the nanoscale, right? And that, of course, is very difficult because it's very difficult to focus light down to length scale smaller than the wavelength of the light you're working with. And in both of these cases, we're also interested in how we can control that light at the surface of the material. So whether that's for coupling to free space radiation, for thermal selective emitters, or whether it's interacting that with the molecule that we bring up to the surface of our structure, in both cases, we want light on the with wavelengths on the micron scale to interact with nanostructures and at the surface of our materials. So when you start talking about light at surfaces, one of the things that immediately would pop to mind would be plasmonics, which is sort of the field of research associated with surface plasmons. Now, plasmonics is a hot field, and a lot of people are worried that it may be one of these buzzword fields because one of the issues with plasmonic structures is, of course, loss. But if you actually think about what we're interested in doing in the frequency range we work in, we actually want loss. Loss is fine, because if you can engineer a loss, that effectively a selective thermal emission when you heat up the object. So in fact, what we're trying to do is engineer losses onto our surfaces and use those, for instance, for thermal emission. Now, there are two types of surface plasmon modes that people generally talk about. The first is the propagating mode that exists at the metal dielectric interface that propagates along that interface, and that's generally referred to as a surface plasmon polariton. You can also get a plasmonic mode that exists on a 3D geometry. It's localized to an actual three-dimensional object in space, and these are generally referred to as the localized surface plasmon resonances. Now, both of these resonances can give nanoscale confinement of your light, assuming that you're working with the right frequency, and the opportunity to engineer optical resonances. But things are very different in the mid-infrared. So in fact, in the mid-IR, using traditional plasmonic metals, such as gold, you can't actually generate a localized, or you can't support a localized surface plasmon resonance. So I'm going to talk about some of the ways that we can work around that by making our own metals. But first I want to focus on these propagating surface plasmon modes. And I want to show you the difference between these modes in the near IR and visible and the mid IR. So the first thing is, if you look at propagation length, you can see that in the short wavelength range, these things propagate from the order of tens of wavelengths. But as you move to the mid IR, they can actually propagate for thousands of wavelengths. That's a good thing, but if you look at the penetration of the mode into the dielectric side of your interface, what you immediately see is you get very strong confinement in the near IR visible, and your confinement is much larger than the wavelength of light in the mid IR. So then it's not surprising that you have these long propagation lengths, because effectively your mode is loosely bound and very little of your mode interacts with the metal. Good propagation length, but of course if you want to enhance your interaction with something at the surface of your structure, this penetration depth is not very good. So I want to give two examples from our previous work which sort of illustrate these points. The first is we're looking at these plasmonic structures, which basically consist of a sub-wavelength slit, which we excite from the bottom side. And that excites propagating surface plasmons along this metal-air interface. So we put in a bunch of these scattering sites, and we use those scattering sites to scatter some fraction of the propagating surface mode into free space. And we design these in such a way that we can actually control the interference pattern of the scattered light above our plasmonic structure. And what you can see is that we can, in this case, we've designed the structure to be able to focus our light at a given point above our sub-wavelength slit. And what you see is that, in fact, we can do that. And the reason that we can do that is because we can use the scattering off of many of these scattering points, because the mode travels for very long distances. So we can actually beam-shape structures in this mid-field region by using the long propagation length of our surface plasmons. But then when we try to actually dynamically control our plasmonic structures in the mid-IR, so this is a structure which is basically a MESFET structure. We have a plasmonic gate under, and under that we have a doped gallium arsenide structure, which we then deplete when we apply a bias, and we change the permittivity of our gallium arsenide. And when we do that, we should be able to tune the optical properties of our plasmonic structure. And in fact, that is what we see. But unfortunately, if you look at the x-axis here, you'll see that we don't tune it very much. And the reason for that is that our plasmonic mode, as I said, is quite large, and we can only tune on the nanoscale. So we can only control the permittivity of 20, 30 nanometers of our material. So you don't have good overlap between your optical mode and your tunable material, which results in very weak tuning. Okay. So what does that mean? Well, it means if we're using traditional plasmonic metals, in a way, we're sort of hamstrung. So the far field properties are great, and they look exactly like plasmonic structures in the shorter wavelengths. But things are very different in the mid and the near field. We have these long propagation lengths. These are weakly bound modes, and we can't get the localization of modes that we really want to be able to interact this light with molecules. And furthermore, because we have these propagating modes, there's an angle dependence to the interaction with free space radiation. So this makes strong confinement difficult. It makes tuning practically impossible. And so we thought, well, maybe we can just fake it. So maybe we can use essentially an array of antennas. Now, this isn't going to give us localization laterally on the sub-wavelength scale, but maybe we can use these to confine our light to a vertical dimension much smaller than the wavelength. So essentially what we have here is a bunch of antennas sitting above a ground plane with a dielectric spacer in between. And so you excite an optical mode that couples to the ground plane, and you get this very strong enhancement inside of your optical field inside the dielectric. And what you see, in fact, is that if you design for a given wavelength, you can, in fact, get almost perfect absorption in these metasurface structures. And when you heat up that structure and you look at the thermal emission, what you see is basically that reflection signal flipped. As you would expect, you see very strong selective thermal emission at your absorption frequency. All right? And because these are localized excitations on these antennas, this is strongly angle independent. Though, of course, this is a 1D structure, so it is polarization dependent. But we can do the same thing for a series of disks, and there you get a polarization independent selective thermal emitter. So this is the result from that structure. And what you see is, in fact, that we've been able to achieve emissivity of over 0.9. So very, very nice emissivity at our design wavelength, and practically zero everywhere else. Right? So the structure is only emitting at the wavelength which we design it for. And furthermore, we know that we're getting very strong confinement of our light in this structure because we can actually see the interaction of our optical mode with a molecular resonance inside our dielectric spacer. And the way that we see that is we actually see an anti-crossing of the two absorption signals from the dielectric material and from our optical mode. And we can actually model that as a coupled harmonic oscillator. We can see it in our numerical simulations. And what it shows is that we have a very strong coupling between our optical mode and the dielectric resonance within there. And we get very strong confinement, at least in the vertical direction, on the order of lambda over 30. So basically all of our light is interacting in this dielectric structure. But what we're interested in, of course, is dynamic control. So there are a couple ways that we can do this. The first thing we could do is we could integrate, instead of using just a dielectric spin on glass, we can use a semiconductor, an active semiconductor structure inside our dielectric spacer. But one other thing we can do is we can actually simply control the thickness of our spacer. So this is a proof of principle where we simply change the thickness of our spacer. And so what you see here, this is the optical resonance. You basically see that we are able to quench that optical resonance. Now what we're doing moving ahead with this is that we're actually designing MEMS structures, which means that we have an air gap, so we're not going to get the material absorption that comes with our thick dielectric spacer. We're actually tuning the position of our top metal layer above the metal ground plane and effectively turning on and off this thermal emission resonance. So we can actually design a structure where we can control the thermal emission dynamically in this 3 to 5 micron range and effectively tune the temperature of our surface. So if you're looking with a camera that operates in the 3 to 5 micron range, you can basically change the effective temperature of your surface by about 100 K, ideally. Okay, so those are sort of fudged metasurfaces, plasmonic structures, because ultimately it's not a plasmonic resonance we're exciting, it's an antenna resonance. So the reason why you can't get these localized plasmonic resonances in the mid-IR using traditional metals is that the real part of your epsilon for your metal is extremely large and negative. Okay? So you're not going to be able to get these types of resonances with gold, but no one says that you have to use gold. In fact, we started thinking, well, maybe we should just make our own metals. And that might just be easier. We know that if we control the dopant concentration in a semiconductor, we can get orders of magnitude change in conductivity. So maybe we can turn our semiconductor into a metal. And maybe we can dope it so high that we can get to epsilon, real parts of epsilon less than 0. So this is work that's done by my postdoc Stephanie Law here at UIUC. And what she showed is, so she grew a bunch of indium arsenide samples by MBE, excuse me. And what you see if you look at the reflection is that as you move to the longer wavelength, so you start off with 30% reflection, which is what you'd expect off a semiconductor surface. And as you move to longer wavelengths, what you see is the reflection moves up to 100%. So the surface becomes essentially perfectly reflecting. It becomes metallic, right? And we can model these thin films using the Drude model. It's actually a very nice model of these structures. It follows the Drude model quite nicely. And what you can see for these 5 different films is that we can actually change the plasma frequency, so the frequency at which our epsilon real goes negative. We can shift that all the way from 15 microns down to 5 microns. So across a good portion of the mid-IR, we can effectively design metals that we're able to grow epitaxially, single crystal, and we're able to engineer the optical properties of these metals. Okay, so what can we do with that? Well, the first thing I want to talk about is what happens before epsilon goes negative, right as it crosses over to negative epsilon. So that's where your epsilon is near 0, or E and Z material. So when your epsilon goes to 0, the effective wavelength of your light in this material becomes extremely large. And it turns out that when you have this very large effective wavelength in your material, you can couple quite nicely to the fundamental TM mode of a sub-wavelength aperture. So in fact, what we showed here is that when you have a thin film of gold with a sub-wavelength slit, in this case about 0.9 microns, right? And you put that over an E and Z slab, you can actually get a very strong enhancement of the transmission through your material. Okay, so it's nice that you see a spectral peak that's associated with this E and Z enhanced funneling. But how does it compare to an actual material? So let's say we use a high K dielectric like gallium arsenide, no losses, so no free carriers in our gallium arsenide, best case scenario for coupling to this small aperture. We actually beat transmission through that gallium arsenide structure with no material losses for our short and very narrow slit structures. So despite all the losses that we have in our material from all these free carriers, we still get more light. So we're essentially funneling this light into our sub-wavelength mode in this very narrow slit. Okay, so that's one of the neat things that you can do at epsilon near 0. But what about when the material goes metallic, right? Can we actually, for instance, sustain a localized surface plasmon resonance on this highly doped semiconductor? And that would essentially show, remember, you can't do that with gold in this wavelength range, right? But that would essentially show that we can make plasmonic nanoparticles in the mid-infrared with all the same properties that these particles have in the visible. And in fact, when we look at an array of patterned particles made out of our highly doped indium arsenide, that's exactly what you see. You see a very strong dip in your transmission that's associated with the localized surface plasmon resonance from these materials. And this matches up not only very nicely with an analytical description of these sub-wavelength particles as sort of polarizable dipoles, but also with our numeric simulations that shows that we have this strong Joule heating, which is where this absorption dip is coming from. So in answer, yes, these materials can be plasmonic at long wavelengths. We can get the localized surface plasmon mode in addition to the sort of the neat physics that we can do in the E and Z wavelength range. So as we move forward, what we're interested in is what can we integrate our mid-IR plasmonic metals with. So we can put them over active semiconductor devices, whether those are indium arsenide, gallium arsenide emitters or detectors, and integrate active material into these structures, as well as making layered plasmonic structures and metamaterials. I have a student, Will Stryer, who's working on highly doped silicon and looking at some of the same things with these very, very small silicon nanorods that he's been able to make. And as I mentioned, we're looking at how we can dynamically control the thermal emission from thin film surface coatings to be able to serve as thermal cloaking devices. So with that said, I'll leave my conclusions up, and thank you very much for your time and attention.
Can you make a comment on the indium arsenide material, because the bender is close to mid-IR, so the loss, is this the best material?
Yes, thank you for asking that. It's a wonderful question. Actually, what's really interesting is that when you dope this material this high, what actually happens is you shift the band gap, and it becomes effectively transparent. So what Stephanie showed is that, in fact, if you look at the band edge absorption in our indium arsenide for the highest doped samples, it actually goes off the range of our FTIR. So what's basically happening is you're filling up your bands with electrons. And so if you shine the high energy light at your device, there's nowhere for that light to be absorbed because all the states in your conduction band are full. So you actually have to go higher and higher in energy to be able to actually absorb that light. So this material actually turns out to be transparent up to telecom wavelengths. So that band gap shifts from 3 or 4 microns out to about 1 micron, or a little bit longer than 1 micron. So that's actually a really interesting side effect of this high doping.
That's very good. But can you also make a comment on p-dop instead of n-dop? Fusion hole instead of
So the reason we went with, so there's a couple of reasons why we went with n-doping. The first is, if we wanted to push the plasma frequency to short wavelengths, and the electrons, I believe, have significantly lighter effective mass, which means that you can push that plasma frequency to higher energies, which is harder to do with the heavier holes. But the other issue is actually indium arsenide And this is some work done at Bell Labs, I think 30, 40 years ago. It's actually, you can really dope it highly degeneratively N-type. And it has to do with this Fermi stabilization level that lies well inside the conduction band. But I think it's harder to dope this highly P-type. I think it gets trickier to dope P-type. Yeah.
Okay, with that, let's thank Professor Wasserman.